Let's continue with some practice with limits in this assignment. So question 1, as we approach 3 from the left side, 3 from the negative side, the y's are getting close to 5, and as we approach 3 from the positive side, the limit of the y's is also 5. So does that mean the overall limit as x approaches 3 is 5? That would be true. This is the very definition of a limit. If the left and the right hand limits agree, then the overall limit is that value. In question number 2, as x approaches infinity, this would be the right end behavior of the graph. It approaches 9. And on the negative infinity side, this would be the left end behavior of the graph. The y coordinates also approach 9. So is x equals 9 a vertical asymptote? That would not be true. That would tell us that y equals 9 is a horizontal asymptote. So completely different. In question 3, we have a rational function, and we can see that 0 is not in the domain. It would cause division by 0. So there's a vertical asymptote at 0. So if we were going to graph this, we would put a vertical asymptote at x equals 0. And we're wondering about the limit as x approaches 0 from the negative side. So next to a vertical asymptote, there's only two things that can happen. The graph can go to positive infinity or to negative infinity. So how do we find out? Here we want to choose a number slightly smaller than 0. So think, for example, what if x happened to be something like negative 0.01? So if we put that value into our function, the numerator would be negative, but the denominator would be positive. So I can see that our graph is going to go down to negative infinity. So this would be wrong. It should go to negative infinity. And in question 4, we're doing the same function, but now we're going to look at the left end behavior as x approaches negative infinity. So what happens on the left end of the graph? Well, our horizontal asymptote is y equals 0 because the degree of the denominator is greater. So we have y equals 0 as a horizontal asymptote, and we suspect this graph is going to go like this, but we better check. Think what would happen if we chose a very small number for x, like negative 1 billion. Can you see that the numerator would be negative, but the denominator would be positive? So it's going to get very close to 0, but it will be negative. So we can see that this is going to approach 0 from the low side. So it is true that the limit will be 0. And in question 5, here we have a function that has a common factor. So if we factor and cancel, we can see that there's not a vertical asymptote at negative 2. There's a hole in the graph at negative 2. So a hole in the graph does give us a removable discontinuity. So this is the same as graphing the line y equals x minus 2, except we have to remember, so it has a y-intercept of negative 2 and a slope of 1. We have to remember as we're graphing it to leave a hole in the graph at negative 2. So when we put negative 2 here, we'll get negative 4 as our y-coordinate, but that's more than we needed to answer the question. Yes, it does have a removable discontinuity at x equals negative 2. And its x-intercept, we've already answered this question by observation. We see that it does have an x-intercept. We want the y to equal 0. When is a fraction equal to 0? When its numerator is equal to 0. So we can see that x equals 2 is going to give us the x-intercept. So not negative 2, but positive 2. And for number 7, a horizontal asymptote, the degree of the numerator and denominator are equal, so our horizontal asymptote would be the ratio of the leading coefficients. So it would be at 4/1, so 7 is also false. All right, number 8, I want to actually show you on the TI-89 emulator, so I'll change screens here in a minute. But what we're going to do is use the table function on the calculator, and we're going to find out, we can see that if we put 2 into the denominator that we would get division by 0. So we know that the function is undefined if we tried to let x be equal to 2. But the question is what happens not at 2 but when we are very close to 2. So I'm going to try putting in some values. And I like to set up my table so it kind of has some symmetry to it as we get closer and closer to 2 from the small side. And then we'll do something similar as we are larger than 2. So I guess I should do something like this. So it kind of has some symmetry, but it doesn't really matter as long as you can see that the values are getting close to the same thing. If they don't get close to the same thing on either side of 2, then of course the limit doesn't exist. So we're going to go to our TI-89 and use the table feature. So I'll close that window for a minute. And this isn't real easy to use this emulator while the video is going, but I think we'll be okay here. So you could go to your Y editor, and I've already put in our function as y1, so you could pause the video and put in the function. Remember to put the numerator in parentheses and the denominator in parentheses. Verify that you have it correct. So once you have your function in the Y editor, then we're ready to set up our table. And there are 2 types of tables, not unlike your previous calculator. When you choose this table set, I did green diamond F4. When you choose this table set option, it looks like there's a lot of mistakes because everything's grayed out, except I see the word ask. And just to show you here, I'm going to hit the right arrow. There are 2 types of table, an auto table and an ask table. And we want to leave it as an ask table. So go down and change that to ask and hit enter. And then we're going to do green diamond F5 to actually see the table. We only have one function, or at least I only had y1, so it's showing me xy ordered pairs, but they're not the x coordinates I was interested in. These just happen to be, sorry, I'm dragging my calculator around. These just happen to be the x values that I was using for some problem previously. So F1 menu has choice 8 to clear the home screen. It also, when you're in a table, F1 choice 8 is to clear the table. So F1 choice 8, and it asks you a question, are you really sure you want to clear the table? So you could hit escape to cancel, or enter if that's what you really want to do. So enter clears the table. And now I can type in this is why it's called an ask table. It's asking me what x coordinates was I interested in. So now I want to do those values that I had typed in. So I'm going to start with 1.99, and it doesn't show up until we hit the enter key. So it's in the entry line, and there it gives me the y coordinate. And this is a little frustrating to remember to hit the down arrow. And then I wanted to do 1 point and then 4 nines. And did I get 4 or did I get 5? I'm going to back up there 1. Let's try that again. Backspace and hit enter. And then I'm going to go down. I'm going to do 1 with 6 nines. And I think I've got 6. Sometimes it repeats here when I'm using the stylus. When we put in 2, I think I know what that it's undefined. And not 23 there, but 2. When I hit enter, and there it says undefined. That's what we knew was going to happen. And then I want to do my 2 point. And then I want to do 1, 2, 3, 4, 5 zeros and a 1. Hit enter. And go down and do a 2 point and then 4 zeros. 1, 2, 3, 4, and a 1. And then I want to go down 1 more column, and I want to do 2.01. And you don't have to do this many, but it shows us, and now I can just scroll up on my table, and we can look to see, does it look like we're getting close on either side of 2? It looks like we're getting very close to 0.75. So if I rounded this to 3 decimal places, you can see that it would be 0.750. So it looks like, even though there's a hole in the graph, an undefined value, it looks like there's still a limit that it gets very close to 0.75. So then you would copy these values into your table. So now I'm going to go back to, and I'm just going to take a minute here and do off on this calculator emulator and go back. So it looked like we were very close to something like these values, and you can transfer them more carefully. I don't remember what was there, but it appears that the left-hand limit and the right-hand limit are both 0.750 if we go to 3 decimal places. So we can say that the overall limit of f of x appears to be 0.75 to 3 decimal places. So remember, we don't know that that's exactly the limit, but it appears to be. So using that table feature. Okay, now there's one other thing up here that you maybe would have noticed. So in this function, notice that there's some algebra. If you were wide awake, you maybe said, hey, I think I can use factoring by grouping in that numerator. Take an x squared out of the first 2 terms and take a 1 out of the, or a negative 1, sorry, out of the second pair of terms. And the denominator, of course, we know how to factor as well. So now we have x minus 2 as the GCF in the numerator, and that would leave an x squared minus 1. And down here in the denominator, we can factor this as x minus 2, x plus 2. And this x squared minus 1 can factor again, but in fact I don't really need to do that. But now notice that we've removed the problem, the 0 over 0 problem. So now to do our limit. Now if we put a limit on that value as x approaches 2, then you can see that this factored form, this canceling solved our problem. So then we could do this by direct substitution. We could plug 2 in, and notice what happens here. If we put a 2 in, our numerator is 1, and our denominator, let's try that again. If we put 2 in, 2 squared is 4 minus 1, our numerator is 3. And when we put 2 into the denominator, we have 4. So in fact, our calculator limit worked out the same as our algebraic method. Okay, but I want you to be able to, we're not always going to be able to factor and cancel, so I want you to know how to use the table feature on your calculator. All right, so some quick work here from a graph. The limit, the left-hand limit as we get close to 2, so we're going to 2 from the left side, so we get close to a y-coordinate of 2. As we approach 2 from the right side, we get close to a value of 0. So since these two do not agree, we know the overall limit does not exist. As we approach 4 from the left side, we're getting very close to 3. As we approach 4 from the positive side, we're getting very close to 3. So the overall limit is 3. Even whether there's a pop point or not, when there's a hole in the graph, that's a removable discontinuity. So we can answer those 2 questions. I just answered the second one. This hole in the graph is called a removable discontinuity. And at 2, in order for those little guys coming down the highway to shake hands, they'd have to make a big jump. That's called a jump discontinuity. So the limit exists at a removable discontinuity, but the limit does not exist at a jump discontinuity. All right, let's see if we can speed it up here now for some practice. If we tried doing direct substitution of putting 1 into this function, you can see that we'd have our 0 over 0 problem. But if we notice that algebra solves our problem, because that denominator is the difference of squares. So you have to know how to factor the difference of squares. We already reviewed that for our competency exams. So once we factor the difference of perfect cubes, now we could use direct substitution, put 1 into the x values, and our limit turns out to be 1/3. In number 18, we're not looking for next to a vertical asymptote, we're looking at the right end behavior. So this is a rational function. Notice the numerator and the denominator are second degree. So our leading coefficients, they're out of order, but it's 4 over -2. So the horizontal asymptote would be at +4 over -2. So our horizontal asymptote, in other words, is what we're coming up with here. All right. And now we've got to review our e to the x graph. Our exponential graph, e to the 0 power is 1, e to the first power is 2.7, and e to the -1, 1 over e is about 1/3, e to the -1. So remember, our exponential graphs have a horizontal asymptote and a key point at 0, 1. So our limit as x goes to -infinity, we're being asked for the left end behavior. So our limit is 0, our horizontal asymptote. In question 20 and 21, we are doing a negative on the x. So that's a horizontal flip whenever you do a negative with the x value. So we know, regardless what the function is, that it's going to be a horizontal flip of the graph from question 19. Still the same horizontal asymptote and still the same key point. Make sure this makes sense to you. If we put -1 in for x, this would be e to the negative, to the opposite of -1. So it should make sense to you why at -1 we're at a value of e. So the limit as x goes to +infinity is our horizontal asymptote on the right-hand side. And our limit as x goes to -infinity, the graph is rising. So over here, the graph is going to +infinity. So it doesn't have a numeric limit. It rises infinitely.